Alrighty, and welcome back. Our next speaker is a longtime data professional, having worked across a range of domains, including such household names as Zillow. He's now a data science manager at General Atomics Intelligence, here to talk about uncertainty. Take it away. Thank you. Applause.
Thanks very much. Thanks so much. It's a beautiful day outside. Lots of things to learn inside. Thanks for being here. Today I wanted to talk about managing uncertainty and errors. I want to give a special shout out to Dr. Owen Beyer, who helped me put these slides together. He helped manage my errors, but anything I misspeak, mistake is mine. So here's a quick look at basically what we're going to deal with today. But if anything, I hope you take away a few concepts of how to manage errors in whatever domain you're dealing with. We're going to talk about tracking today. It's kind of a niche area. However, I hope you find some concepts or other things that you can find apply to what you're working on. All right, so math in textbooks is great, and Calc 3, if you remember those days, you're like, wow, this is how we predict the weather, but there's other things that happen, right? Maybe all of you sports ball folks did the probabilities of who's going to win the NCAA tournament, and your brackets got blown up like first or second round. We all like to complain about the weather person was wrong once again. Medical devices like glucose monitors can be off 10 to 20% for any given reading. And I don't know about you, but many of us have probably experienced some sort of GPS issue like you see on the screen right here. Well, there's a lot of problems in the real world, and so when math meets the real world, there's issues to go manage. In tracking specifically, there's some interesting issues that I'll get into, but I feel like I need to explain what tracking is. Basically, there's equipment somewhere and you want to know where it is, right? It's simple, whether it's an oil tanker in the ocean or an airplane flying over the middle of the US, you want to know where it is. There's two ways to do that. There's two ways to approach it. First is the calculus of where that thing is. It was headed in some direction, it was going at some speed, and so where do we think it probably is at any given time? The second way is maybe there's an instrument that is tracking the thing. So radar, GPS, ocean has AIS, commercial airlines have ADS-B, and so that can help in terms of where the thing is. Where did it observe that particular object? Now, one thing I do want to mention is this wasn't intuitive to me, so I'm going to pause and take a minute to describe it, but it was odd to me that we're talking about a prediction of where something is. And it's like, well, I'm looking at the screen, it's right there, right? Like the radar just swept through, isn't it right there? It turns out that's not always the case. So think about it this way, an off-the-shelf drone, something that a hobbyist might use or that photographs commercial, real estate that goes on Zillow or something like that. Can travel up to 30 to 50 feet a second. So if one was flying right above me, it's already out the theater. And by the time I reach the end of the sentence, it might even be 4 blocks east, somewhere approximately over New Dominion Bookshop, right? So things travel fast. Think about when you're starting to track airplanes. The commercial aircraft can be 800 feet a second at cruising speed. And when you're getting into fighter jets, you're talking about 2,000 feet a second. So where something is, counterintuitive to provide a prediction for that, but there we are. The great thing is you can have your cake and eat it too. You can provide both the physics-based expectation of where something is, as well as information about that object that we've observed in the real world. You can combine both with a Kalman filter, and it becomes a really powerful way to solve this problem. Now, I'm not going to do the math. There's a lot of notation for it, and it depends on what dimension you're working in, et cetera, et cetera. If you are interested in that math, I highly recommend Stone Soup. A lot of great tutorials, very math heavy, and you have a Python library at your fingertips if you find this particular thing interesting at all. Now, assuming we have a history of an object going already. We have a prediction of where that thing is. There's a point estimate, that little dot on the screen, and around it is an error estimate, an ellipse, to say, this is roughly our uncertainty of where it could be. Now, we get a measurement in. It could be GPS, it could be radar. We have some new information about that object. The gap between the 2 point estimates, where the sensor says it is versus where we predicted it to be, that's the innovation. What do we do with that gap? We have to reconcile those two. Well, we make an update, and this is a gross overgeneralization, but we basically take a weighted average effectively as one way to think about it. A lot of stuff going on there, however, it's an easier way to think about it. And then the cycle starts all over again. All right. Now, remember, we're also feeding the physics-based expectation of where that thing will be into this model. There's 2 parts to the common filter. It's important to note that not one motion model fits every single situation. So some sort of cargo ship in the open ocean is going to be a lot different than a plane taking off. So for the cargo ship, you might do something called a constant velocity model. But if an airplane is cruising and starts turning, you might need to switch to a higher process noise. Still constant velocity, but a higher process noise is more appropriate. Now, you might be thinking, what is process noise? Yeah, exactly. I had the same question. There are a lot of errors and issues common to tracking. Spoiler alert, it is not like the movies. So everything from Independence Day to Mission Impossible is completely unrealistic in terms of how things work right now in the real world. And so, someone says, I have something on radar. Trust me, most likely there's a lot of things happening on that radar at any given moment. This thing is coming towards us, and they perfectly know exactly what it is. That doesn't happen. There's a lot of work to ascertain the identity of that object. There is a reason we joke about flocks of geese versus Cessna planes, right? That happens, okay? Or I'm locked on, we see this object coming towards us over the 5 minutes of the movie or whatever. No, every moment that passes, the uncertainty that that object is the same thing you just saw a few moments ago grows. So your errors are compounding, right? Is it really the same thing you thought it was? Those 2 blips on the screen might not be it. So like I mentioned before, there's a lot of errors in tracking specifically. There's 2 really gnarly errors, and they break out into the motion model uncertainty and the sensor uncertainty. So for the motion model, how is the thing moving? A train, that's pretty easy. It's on a tracks. There's only a couple of directions it can go. And depending on what continent you're on, it probably is moving pretty slow. So you have an easier time of knowing where that thing is. Cars introduce other components. The driver can make decisions. They might be in the city or on an open highway, so there's a medium process noise. Drones, highly maneuverable, and so there's a much larger process noise there. However, there's also a measurement noise. So, even the best sensors have errors in them. And so very high quality radar might be within a few feet to a few meters, but your GPS device on your phone, for example, it's going to start behaving differently, whether you're in downtown Charlottesville or you're in the urban canyon of Manhattan, right? And so the errors are there. Roughly speaking, for our domain, the good news is you can approximate a random normal distribution. There's other issues, but it's pretty effective for us. And so, there can be roughly a bell curve over how some of these things break out in terms of the range of errors for them. But it doesn't end there. There's always other issues. Data association. Think about this. This has happened, in movies. Is it one blip on the screen, or is it a formation of fighter jets that are really more than one? There's multiple instruments. If you have 2 radar systems, how do you know one dot on one and another dot on the other is the same thing? Especially when I mentioned there's a lot of things flying around, right? The other one is out of sequence measurements. This is just painful. It really is, like even this week I was in a meeting, there was a lot of heated debate around how to handle this. So it is what it is. And then even worse, there is many permutations of all of the above: process noise, measurement noise, and then anything you see on the screen right now. So what are we gonna do? There's a lot of noise. I want you to take a moment though and think about what is the noise in your domain? What's the issues in your domain that you're experiencing? If we just take a moment to pause and say like, oh yeah, that thing at work is really bugging me, right? Let's take a step outside of tracking and let's think about your domain. What is that thing that you are just really having trouble wrapping your arms around, right? Well, here's a few ideas. Here's how we've done it, but hopefully you get a few ideas on how to maybe manage it in your own specific case. One thing I want to do is, even though we're at an applied machine learning conference, there's tools outside of machine learning to start to make the problems tractable. One of the things that has saved me in a number of different situations is the MECE framework, mutually exclusive, collectively exhaustive. And it's basically making sure you can start to pick apart the problem in a way that you have a collectively exhaustive set, but every part is mutually exclusive. So again, to step outside of the tracking domain, let's talk about retail for a second. You might have a CEO who's really upset about their revenue is down. Okay, there's going to be all sorts of voices at the table saying it's because of this, it's because of that, marketing didn't get enough budget, blah, 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 blah. Let's stop for a second. Revenue can be decomposed into volume of units times price. Okay, there's two things we can deal with now. Now let's look at each one of those, okay? With units, maybe in-store traffic was down and we sold less there. Okay, that's another piece that we can start to break down. On the price side, maybe there's a lot of competition. Maybe there's a lot of promotions that were in market, right? So you can start to see the tree in your head of decomposing all of these difficult parts into their subcomponents, right? The good news is that starts to give you a roadmap to deal with some of these problems. For us in tracking, some examples is the trajectory, the path something followed, synthetically generated, or did it come from an actual sensor? Is there a ground truth available or not? Is the model matched to the motion model? Remember, there's more than one. Or is it a realistic trajectory? When you start to get all of the permutations of those, you see something like what's on the screen. This is not an exhaustive list, but it's relatively comprehensive in terms of what we actually deal with. And the nice thing now is not only do you have a roadmap of starting to pick apart this problem that I asked you a few moments ago, what's bugging you, you can start to be more methodical in your approach and have a checklist. Checklists feel great, right? When you start checking things off, it's like, yeah, you got something done. What I'm going to talk about specifically today is the algorithm validation. And so this is one of the more important pieces for us. Why start there? For us, controlled environments isolates a number of different areas. The ground truth helps us measure something objectively. We're not making this up. We can compare it to something. And then honestly, when you're doing applied math, it would feel pretty terrible to ship code that has a mathematical error in it. Like, the starting point doesn't feel good. So how do we do this? Let's start to get in a little bit of the nuts and bolts. We have some made up trajectory here. I don't know, let's pretend it's a drone, and while there's some turns, maybe these are really wide arcs. So maybe a constant velocity model with medium noise. Okay, we've made this up, right? We made up the truth. That's great, because now we have a baseline to use. From that truth, we start to make a number of simulations. And so we have a catalog and understanding of different sensor profiles. GPS has this error profile, ADS-B has this error profile, on and on and on. Now we can randomly start to make more and more simulations. So now we're having a realistic, random, normally distributed noise. This is the Monte Carlo part, right? And so now we can start saying it is not luck of the draw. As we go through the process of calculating the differences between the ground truth and these simulations, the average, these things should effectively average out. And we have a way and a path to understanding, can we have statistical confidence in what we're doing here? Now, in our scenario, we take these simulations, we leave out the ground truth, and we pass each one of these simulations through our platform, our tracking platform. And then we get output for how the thing actually did. So let's say we have, just this is a completely made up data set from time t to time t plus n. We have the actuals and the estimates side by side. So the lat long, maybe altitude didn't fit on the slides, but we can compare the ground truth to the tracker output, the actual estimates. Now, this is the wall of text. This is a little more difficult. I'm only a few months in. I'm still learning the ins and outs of some of these, but what I can tell you is that the nice thing about common filters is they provide a prediction and an estimate of how uncertain it is about that prediction. So now that we can combine that with ground truth, there are a few interesting things we can do. ANIES is one way we can measure the issues. And this is more about is the common filter accurate in how it's estimating its own uncertainty? If you remember back, way back in the slides, there was an error ellipse, right? The common filter is providing that error ellipse. It's telling us how uncertain it might be. Now we have a way to checking, were you right? And so if we were dealing with a situation that is tracking latitude, longitude, and altitude, that is 3 dimensions. We expect an average NIES of 3. If it's above that, the common filter is overconfident. If it's below that, it's being a little too cautious about its uncertainty. RMSE is a little more intuitive, physical distance between the actual truth and that point estimate. And then you have containment. How often was the true position inside that error ellipse, right? There's many other metrics you can use in tracking, many other things to think about, like state association metrics. These are state estimation metrics. But take a moment to think, what might be useful for you in terms of metrics for judging whether or not your algorithms are performing how you might want them to. Now, for us, we have 2 ways of testing whether or not we're actually introducing regression errors or bugs into the code. Again, this is just algorithmically. First, we have a CI/CD pipeline. So if the platform is going through a build, once it reaches the end of that, it triggers a downstream job. And we have version-controlled YAML that define different scenarios and number of scenarios. And we chug through them, each one of those scenarios. The output is then stored as an HTML artifact in GitLab, and you can even have drill downs into different things to see either troubleshoot or just get more information. Local development is interesting. This has been one of the more fun parts of it, is building a CLI tool to help developers understand as they are changing, making changes, how things are performing. So the platform itself is not static. We are tracking things that move. So what we do doesn't stay still either. We're changing out motion models. Sometimes we get academic research about different variations of common filters, and we start implementing that, right? So as people are taking that from paper to code, we want to make sure the algorithm is correct. And so whether they're in a notebook environment or more like a terminal shell script environment, they can call this tool and make sure that they are not introducing any errors. The nice thing is we also add some other optimizations to make this run faster and faster and continue to gain ground on it. In both of the scenarios, the law of large numbers starts to take effect. And so we start to have confidence intervals around the problem, so we can actually say, hey, this passed or this failed. And usually we do start with like 100 simulations per scenario, just to give you an idea of how often or how many scenarios we have to run. This is a screenshot. I don't have a demo today, but this is a screenshot of the output from the CI/CD pipeline. On your left are two different scenarios. You can see the green means they passed. It's hard to see the actual numbers, but you can see to the right, the target is around 3. And even though things are bouncing around throughout the simulation, it is still relatively close to what we were targeting. And so these scenarios passed. This might be what someone might see in the notebook environment. So on the top left, we have a completely made up synthetic trajectory. On the right, we are continuously randomly drawing more simulations on top of that ground truth, again, mimicking the different noise and bias and measurements that you might have from different sensors. That is then run through, we've basically extended pandas, and that's been a lot of fun to do, and have a summary that is provided from that extension of how the simulation went. You can see the 3 metrics I mentioned for state estimation here. So there's average knees, there's the RMSE and the containment. I want to call out this first row specifically. You can see the estimate for this simulation was 3.05 effectively. To the right, though, you see the upper and lower bounds of the confidence intervals. And so the fact that this 3.05 is contained within that upper and lower bound means that we are starting to be able to move away from the uncertainty and have more confidence that, hey, when we took from paper to code that math, we did the algorithm correctly for this scenario. So now we can share that and keep iterating on different parts of what we're trying to do. So that is a whirlwind tour of tracking and how we manage just one small component of the different things we need to test. The team made fun of me when I said this very technical phrase, but is the math mathing? Like, that is the one part we're trying to ensure. Future improvements, that table had a lot of things on the checklist, so we are going to start covering additional cases. Because of that, we're going to evolve this small tool into its own library. And there is, as you can imagine, many different permutations. Once you're dealing with the physics and the calculus, along with all of the measurements and the common filters putting those things together, there's a lot of different permutations in how you can tune for specific scenarios. And so Optuna is a really interesting tool that you can do multi-objective optimization. There's all sorts of areas and entry points that you can start scaling that tuning to make the performance better. But that's something we're already exploring and going to start extending. All right, and that is a wrap for me. I finished early, so I guess I have some time for questions. Luckily, some of my colleagues are here just in case you have math questions.
Yeah, so we have about 6 minutes. So if you have questions, please.
How do you know that all your errors are normal? You said that kind of in the beginning.
How do I know the errors are normal? I will tell you up front that remember the table, the specific scenario, because we're controlling it that way. It's a little tautological, but we control the environment, so we're going to do normal errors. Like in the real world, stuff happens. You start to get some really gnarly outliers. But my understanding is because we're dealing with physics, warp drive doesn't exist yet. And so, roughly, like whether it's sensors or the physics, we're dealing with approximately normal distributions. I don't know. Nate, is that would you? Yes, no?
Yeah, I mean, I think, okay, yeah. So there's probably a longer answer to this question. You can talk to, Alex used to work with us, too.
Oh, okay.
So yeah, I mean, I think we are controlling the errors here. And again, part of the point of doing the simulations this way is so that we can verify that that the algorithms we've implemented, which make that assumption, are correct. You can violate that assumption, and sometimes that does happen in the real world. One thing is that like if you make your variance on your Gaussian big enough, you're probably okay. It's probably not the optimal thing to do at that point, but your uncertainty is probably still okay. The second thing is there are extensions of the Kalman filter that actually handle that stuff. So I don't know if we've implemented that necessarily, but things like the unscented Kalman filter are techniques that would handle that.
Cool. I saw another question somewhere.
I think she said it got
Oh, yeah, okay.
Yeah.
Great. Yeah.
So I don't have a ton of experience with Kalman filters, but I know there are some like assumptions you have to make on like any motion-based transform, something like that. Have you thought about at all like coupling it with like more of an ML approach, like maybe using an LSTM for like track prediction in combination with like a Kalman filter?
I would like, there's interesting things we could do. I think the PhDs here have some different opinions maybe, but, weather, wind gusts, all sorts of things like time of day, like how busy an area is. There's a lot of things we could do, I think. But I don't know, Owen or Nate, if you have any yeah.
I can try. It needs to be psychotically fast. We need to be doing, so that's one thing. The other thing is that working with GPUs, there's a lot of CPU calculation that we need to do. So we've talked a little bit about the extent that we can leverage GPUs. I think right now we're still unsure whether the moving things from the GPU and CPU and that overhead buys us a whole lot. And then there's a lot of calculations that we have to do that aren't really GPU optimized also. So yeah, it's a good, it's a topic we're exploring, but we're not sure.
Cool. Yeah, makes sense.
Cool. Sweet. Yeah.
Sorry, just how well does taking this and then actually taking these things and applying them back out into the real world, like how well do you guys end up doing? Because in my line of work, right,
Yeah.
we doing that, right, as soon as we, right, regardless of how well we can get the math to math, right, in
Yeah.
the simulation world, the moment that we jump it back out to the real world, right, you do start to get, right, more often than not, you hit the anomalies, and how do you deal with those?
Yeah, I think one thing is to go back to like what problem are you solving first. So for example, one of the examples on here is, do we have a measurement, a real world with ground truth, for instance? It's extremely rare for us to be able to get ground truth from something flying, that we have a sensor inside of it and we're observing it through the system. But it is a row here, right? And so that is one thing to think about, is again, how do you decompose all of this? So I don't know. That's one aspect. I don't know if, yeah. It looks like, go ahead.
Yeah. Ultimately, tracking has a long history and literature on it, and so lots of people have encountered lots of different problems. Ultimately, what we do in the trackers is we compose a bunch of algorithms together to deal with a lot of the challenges that we face, and that's part of the purpose of this. Is that some of these simulations and that we're doing is we're simulating several anomalies together and verifying that we still get the correct answer at the end. And in the cases where we do have ground truth, it is rare, but it does happen. Sometimes we have truth surrogates. It's not exactly ground truth, but it's still pretty high quality. It has been surprising to me to find that this stuff works actually in the real world.
Yeah. Cool. Awesome. Any other questions? Otherwise, all right. Thank you so much, everyone.
Yeah, let's give a hand. Thank you. Thank you, Adrian.